Hello, I'm Professor Afshar at Glendale Community College. This is Physics 103, Lecture 50. In this lecture, we'll discuss heat engines and heat pumps. This topic is covered in Chapter 22 of our textbook by Surway and Jouet. In the previous lecture, I explained that we're interested in using thermodynamic cycles to perform work. The work performed in a thermodynamic cycle is equal to the area enclosed by that cycle. Of course, we can traverse the cycle in the clockwise direction or the counterclockwise direction. Any machine or device that uses a thermodynamic cycle in the clockwise direction to perform negative net work is referred to as a heat engine. And any device or machine that uses a thermodynamic cycle in the counterclockwise direction to perform positive work is referred to as a heat pump. In this lecture, we'll discuss heat engines and heat pumps separately and in much greater detail so you can understand better when each one of these would be used. Also recall that we are talking about thermodynamic cycles, so the change in the internal energy is always equal to zero, basically because at the end of the cycle, we're ending up exactly where we started. According to the first law of thermodynamics, the change in internal energy must equal to Q plus W. If the change in internal energy is zero, then Q net plus W net must also equal to zero. What this equation implies is that there is a balance between the net work and the net heat that is transferred into or out of a system. If W is a large positive number, like plus 1000 joules, then Q must be a very small negative number, like minus 1000 joules. So thermodynamic cycles are used to build either heat engines or heat pumps. In technological terms, the practical difference between heat engines and heat pumps is that heat engines are usually used to perform work and therefore bring about locomotion, while heat pumps are usually used to transfer energy from something cold to something hot. For example, a steam engine is an example of a heat engine. It performs negative work while bringing about the motion of something. You could use a steam engine to move a train, or you could use it to move a steamboat or an electric generator, for example. A heat pump, on the other hand, is just transferring energy. The refrigerator in your kitchen or the air conditioning unit in your home is an example of a heat pump. There's still work being performed, however, the primary purpose of the refrigerator is to transfer thermal energy in or out of your home. If you're using the air conditioning system to cool your house, then thermal energy or heat is being removed from your house and pumped into the outside air, for example. Now we'll talk about heat engines and heat pumps separately and in more detail, but we'll use the same framework to discuss both of them. The framework that we'll be using is as follows. First of all, for any thermodynamic cycle, whether you want to talk about heat engines or heat pumps, we always need a system, and we'll refer to that system specifically as the working substance. So if you're, for example, talking about a steam engine using the Rankine cycle, the working substance is simply steam or water in the gas phase. On the other hand, if you're talking about an internal combustion engine using the Otto cycle, then the working substance is a mixture of air and gasoline. If you're talking about heat pumps, like a refrigerator or maybe an air conditioning system, for example, in your car, then the working substance is a hydrofluorocarbon, usually referred to as HFC 134A, and in older refrigerators, it might be referred to as Freon. The point is that there is always a working substance, usually a liquid or a gas, that we're going to manipulate using thermodynamic processes. There's also always a hot reservoir. So in addition to the working substance, there must be another system that is relatively hot, so its temperature is higher than that of the working substance, and we'll refer to that system as the hot reservoir. We'll denote its temperature as T sub H. The hot reservoir will be used for the transfer of thermal energy. So we'll have some Q heat that is being transferred into or out of the hot reservoir relative to the working substance. In addition to the hot reservoir, there's also a cold reservoir. So there is another system, a third system, whose temperature, relatively speaking, is lower than the working substance. Its temperature is going to be denoted as T sub C. There's also going to be some transfer of thermal energy or heat between the working substance and the cold reservoir. We'll refer to that as Q sub C. And at the end, whether we're talking about heat engines or heat pumps, there's always some work involved. The work might be positive or it might be negative. As we'll see, for heat engines, the work is negative, so there is an output of energy, whereas for heat pumps, the work is positive, so there's an input of energy. So we'll go into this in more detail, but this is essentially the framework that we'll use for any thermodynamic cycle that is used to build either heat engines or heat pumps. Throughout all of these processes, remember that the first law of thermodynamics must be obeyed for the cycle. Since delta E is equal to 0 for a closed cycle, Q net plus W net must equal to 0. Here, to simplify the notation, I've dropped the net subscript on W, and it must be understood that this W is the net work that is performed after the entire cycle is complete. The net heat can be separated into two components. I've written them as QH and QC. I want to be able to speak separately about the heat that is drawn, for example, from the cold reservoir and the heat that is drawn from the hot reservoir. QH plus QC is basically the net heat, and the net heat plus the net work must equal to 0 for any thermodynamic cycle. So far, our discussion has been quite general, but now let's specifically talk about heat engines. Any device that outputs work by transferring heat from a hot reservoir to a cold reservoir is referred to as a heat engine. So we'll represent a heat engine using a diagram like the one shown here. We have some working substance, which constitutes the main body of the heat engine. We have something hot and something cold, referred to as the hot reservoir and the cold reservoir. We have a transfer of thermal energy from the hot reservoir into the heat engine. Notice in this case, QH is a positive quantity because it's an input into the system. We also have a transfer of thermal energy from the heat engine to the cold reservoir. This is an output relative to the heat engine, and therefore QC is negative. There's also an output of work. When work is output, the energy of the system goes down. That tells us that W must be negative. So a heat engine performs negative work, as we've discussed before. Now, if the heat engine that you're talking about is a steam engine, then the hot reservoir specifically is basically burning coal or burning wood. The cold reservoir specifically is the ambient air. So when a locomotive is moving using a steam engine, it's transferring heat from the coal into the working substance, which is steam. The steam performs some work, that's negative work. The output of work is used to move the train forward. And some of the exhaust is then released into the ambient air, which is the cold reservoir. If the heat engine that you're talking about is the internal combustion engine of a gasoline car, then the hot reservoir is basically the exploding or combusting gasoline mixture. And the cold reservoir is either the ambient air or the radiator fluid that is keeping the engine cool. Of course, ultimately, the radiator fluid releases its thermal energy to the ambient air, so we can say that the cold reservoir is ultimately just ambient air. Now, these are the two examples that are probably most common, but heat engines have many other applications as well. Nuclear power generators, for example, can also be viewed essentially as heat engines. In that case, the hot reservoir consists of uranium rods. So radioactive uranium rods can release a huge amount of energy. The cold reservoir in this case is ambient water. So the radioactive uranium rods are basically used to heat water. The water turns to steam, so the working substance in a nuclear power plant is once again steam. That steam is then used to move something, specifically an electric generator. And then the exhaust is released back into ambient water, which is the water in a river or an ocean that is nearby. Since nuclear power plants use ambient water as the cold reservoir, they must always be constructed near a large body of water, like a lake or an ocean or a river. Regardless of what kind of a heat engine you're building, the process essentially is always the same. A transfer of thermal energy from a hot reservoir into the heat engine, into the working substance, and then an output of energy into a cold reservoir and an output of work that is then used to move some object like a train, like an automobile, or an electric generator. So now let's talk about heat pumps in a little more detail. A heat pump is any device that transfers heat from a cold reservoir to a hot reservoir through an input of work. We can represent a heat pump using this diagram shown here. Notice that this diagram is very similar to the diagram we used for heat engines. The main difference is that the directions of these three arrows are now reversed. So energy, thermal energy, is being transferred from a cold reservoir into the heat pump, and therefore this represents an input of energy. There's also work being performed, and the work also represents an input of energy. The net result is an output of energy. Thermal energy will be transferred from the working substance into a hot reservoir. So the three arrows have reversed direction, and the corresponding quantities are now opposite in sign. For example, for a heat engine, work is negative, but for a heat pump, work is positive. Also notice that for a heat pump, thermal energy is flowing upstream, so to speak. In other words, thermal energy or heat is flowing in the opposite direction that it naturally or spontaneously follows. Normally, thermal energy or heat flows from hot object to cold objects, but we can use a heat pump to reverse that flow so long as there is an input of work. You can use a heat pump to build a refrigerator or a freezer, like the one that's found in your kitchen, for example. In that case, the working substance might be something like a hydrofluorocarbon. The cold reservoir is the icebox, the cold interior of the refrigerator or the freezer, and the hot reservoir would be the ambient air. So in the case of a freezer, for example, the heat pump is taking thermal energy from the icebox, from the interior of your freezer, and pumping it outside into the ambient air. In fact, if you put your hand behind the refrigerator in your home, you'll feel that it's quite warm. The warmth that you're feeling is basically the thermal energy that has been pumped out of the icebox and is being pumped into the ambient air in your kitchen. So while the inside of the freezer or the refrigerator gets colder, the air outside in your kitchen is going to get warmer. Of course, in order to move thermal energy from something cold to something hot, we need an input of work, and that's why your refrigerator or freezer must be plugged into an electric outlet. The electricity operates a compressor, and it's the compressor that is performing work on the hydrofluorocarbon inside your refrigerator. You can also use a heat pump to build an air conditioning unit or a heater. In fact, most modern homes use a heat pump like the one shown here. You might see something like this on the roof of your house or in the backyard. If the heat pump is used to build an air conditioning unit, then the cold reservoir is the interior air of your home, and the hot reservoir is simply the outside air. So a heat pump that is used as an AC unit is basically taking thermal energy from inside your home and pumping it outside. So the interior of your home becomes a little bit cooler while the outside becomes a little bit warmer. Of course, you can also reverse the flow of air in the heat pump. In that case, the heat pump functions as a heater. The cold reservoir becomes the outside air, and the hot reservoir becomes the interior air. In that case, the heat pump is basically taking thermal energy from the outside during wintertime and pumping it into your home, making the inside a little bit warmer. From the previous slide, you may have noticed that a heat pump can be used in two different ways. A heat pump can be used either in cooling mode or in heating mode. In either case, we're talking about a heat pump that essentially pumps thermal energy from something cold to something hot. The real difference is the practical utility or the practical function of the heat pump. If you're using a heat pump in a cooling mode, then you're essentially pumping energy from the inside of your home to the outside of your home. You would use a heat pump in cooling mode during the summertime, for example, to cool down your home. As you move thermal energy from the inside to the outside, you make the inside cooler while you make the outside just a little bit warmer. Now, you can use the same exact heat pump in heating mode by essentially reversing the plumbing. So you essentially reverse the direction of the fan or the flow of air, but the essential thermodynamics is the same. You're once again pumping heat from something cold to something hot, but in the heating mode, something hot is the interior of your home and something cold is the exterior of your home. So when you use a heat pump during the winter time, you're transferring thermal energy from the outside into your home. Your home becomes warmer and the outside air becomes just a little bit cooler. In both cases, notice there's an input of energy through work. So work is a positive number in both cases. And in both cases, thermal energy is being pumped in the opposite direction that it normally flows. So thermal energy normally, spontaneously flows from something hot to something cold, but a heat pump, thanks to this input of energy through work, is capable of reversing that flow of energy. So when constructing a heat pump or a heat engine, one thing that we're very interested in is the amount of work that is performed. In addition to that, we also like to know what the efficiency of the engine or the heat pump is. Very generally speaking, efficiency can be defined as the ratio of some output to some input. The output is usually a useful or desirable quantity which we want to maximize. So the output usually in this context is the good stuff that we want more of. The input in this context is the thing that needs to be minimized. It's the thing that costs energy or money. It's the thing that we would like to minimize as much as possible. So when we say something has high efficiency, what we're really saying is that the output, the good stuff, is a very large number, but the input is a very small number. On the other hand, when we say something has low efficiency, we're basically saying that the good output is a small number, but the costly input is a large number. So we'd like to apply this general concept to heat engines and heat pumps. Recall that a heat engine involves the transfer of thermal energy from something hot to something cold, and the net result is an output of work. This work is a negative number because it represents a decrease in the internal energy of the working substance, but it's also the thing that we want more of. It's this output of work that can then be used to move a locomotive or an automobile or an electric generator. In the case of a heat engine, QH is the thing that is costly. For example, in an internal combustion engine, the hot reservoir is the exploding gasoline mixture, And gasoline is a costly commodity. We'd like to minimize the cost or the usage of gasoline, so we'd like to minimize QH. Therefore, when it comes to heat engines, people define the efficiency as W divided by QH. Now, efficiency is always viewed as a positive number, so we ignore the fact that some of these quantities could be positive or negative. We simply put everything in absolute value signs. So the efficiency of a heat engine is the ratio of W, that's the useful output, to QH, that's the costly input. We hope to build engines that can give us a very large amount of work with a very small amount of QH. We can use similar ideas for heat pumps, but the situation is a little more complicated for heat pumps because heat pumps can be used in cooling mode or in heating mode. Recall that for a heat pump, thermal energy is being transferred from something cold to something hot, and in that process, there is an input of work. It's the input of work that costs us money. In the case of your refrigerator, for example, the input of work corresponds to the electricity that your refrigerator uses to operate the compressor. So W is the thing that we want to minimize, and therefore we place W in the denominator. Now, if you're using the heat pump to cool your home, then QC is the thing that you want to maximize. If you're using the heat pump to heat your home, then QH is the thing that you want to maximize. So for a heat pump, its efficiency in cooling mode is defined as QC divided by W, but in heating mode, the efficiency is defined as QH over W. Now, efficiency is traditionally a number between 0 and 1, or 0% and 1%. It turns out when you do the calculations for a heat pump, this ratio of QC over W or QH over W can be greater than 1. For that reason, people often don't refer to these ratios as efficiency. Instead, they refer to them as the coefficient of performance. So these ratios still characterize the performance or the quality of the heat pump, but because these numbers can be bigger than 1, they are simply not referred to as efficiency, they are referred to as coefficients of performance or COP. The coefficient of performance is a number between 0 and infinity. The higher the COP is, the better the heat pump is. In our discussions of heat engines and heat pumps so far, you've probably noticed that the two are quite similar, the main difference being in the direction of flow of energy, or essentially the sign, positive versus negative, of each one of the three quantities involved, QH, QC, and W. So it's kind of important that you pay attention to the signs when you're doing actual calculations. Recall that a heat engine follows a thermodynamic cycle in the clockwise direction. For a heat engine, QH is a positive quantity because it represents an input into the working substance. QC is a negative quantity because it represents an output. So we can say that the working substance is losing thermal energy to the cold reservoir, therefore QC is negative. W represents an output also, and therefore W is negative. We can say that the working substance in a heat engine is losing energy through an output of work, and therefore W must be negative. When the thermodynamic cycle is followed in the counterclockwise direction, then we have a heat pump. For a heat pump, QH is a negative quantity because it's an output, QC is a positive quantity because it's an input, and W is also a positive quantity because it is some input of thermal energy through work. Now recall that according to the first law of thermodynamics, energy must be conserved, and therefore we can say that the change in the internal energy of the system, of the working substance, is equal to Q plus W. Here, Q really refers to the net thermal energy that is transferred in or out, and W refers to the net work that is performed through the entire cycle. I've simply dropped the subscript net for simplicity in this context. Now, since we're talking about thermodynamic cycles, since we're ending up where we started, the change in internal energy must be zero. So for any cyclic process, we can say Q net plus W net must equal to zero. Now, as you've seen for both heat engines and heat pumps, there's always something hot and something cold that is transferring energy in or out of the working substance. So we can take Q net and break it up or divide it into two pieces. There's QH and QC. QH is the thermal energy that is being transferred into or out of the hot reservoir, and QC is the thermal energy that is being transferred into or out of the cold reservoir. Now, so far, as you can see, the equations are the same for heat engines and heat pumps. But of course, once you start plugging in numbers, you'll notice some differences. For engines, QH is a positive quantity, so we can say QH is equal to the absolute value of QH. But for pumps, QH is a negative quantity, so QH is equal to the negative of the absolute value. Similarly for QC, engines have a negative QC, so QC is equal to the negative of the absolute value. Remember that the absolute value is always a positive, so you need to explicitly put a minus sign in front. But for heat pumps, QC is already a positive quantity, so we can say QC is equal to the absolute value of QC. So we get two slightly different equations. But of course, if you look carefully at these equations, you'll see that the bottom one is simply the negative of the top one. So you can rearrange these equations and say that whether you have an engine or a pump, the absolute value of QH is equal to the absolute value of QC plus the absolute value of W. So you can use either one of these two equations in red. Some people prefer to talk about only absolute values, in which case you should write the equation as shown here at the bottom. Some people are comfortable talking about positive or negative work, in which case you can write the equation as shown here. Both of these equations apply to engines and pumps. The only subtlety is that when you start plugging in numbers, you might find yourself getting confused by all the negative signs that are floating around. In that case, I recommend that you use this form at the bottom of the slide. Let's end this lecture with a practice problem. A heat pump, when used as a heater, has a coefficient of performance equal to 4.2 and requires a power of 1.75 kilowatts to operate. Part A of this question asks, how much energy does the heat pump add to a home in 1 hour? Now notice we're talking about a heat pump, so we're going to be transferring thermal energy from something cold to something hot. We're using the heat pump as a heater, so we're using it in heating mode, which means we're going to be transferring thermal energy into the home. In this case, the home operates as the hot reservoir. Also recall that a heat pump requires an input of work. In this particular problem, the input of work is not given to us, but the input of power is provided. We're told that the heat pump requires a power of 1.75 kilowatts to operate. Recall that watts is equal to joules per second, and a kilowatt is just 1,000 joules per second. So if this heater, for example, is plugged into an electric outlet, the electric outlet will have to provide 1.75 kilojoules of electric energy every second to operate this heat pump. That's the input work that is required per second. A little more precisely, recall from your mechanics course that power is defined as the change in the energy of a system divided by the time required to implement that change. In this particular case, the energy of the system, of the heat pump or its working substance, is changing because of the work that is being performed on it. So we can replace delta E by work. Rearranging this formula, we find that work is equal to power times time. And now we can multiply those out to find that in 1 hour, the work that is input into the heat pump is 6.3 times 10 to the 6. It might be useful if you paid attention to the units that are being used in these calculations. In this particular problem, delta T is given to us as 1 hour, but of course the hour is not the SI unit, so we'll have to substitute time as 3,600 seconds. And power, of course, is given to us as 1.75 kilowatts. It's better to write that as 1.75 times 10 to the 3, that takes care of the kilo, and I'll write the watts as joules per second. When I write it like this, I can see that the seconds cancel out, and I'm left with joules, which is exactly what we want. So we find that in this particular problem, the work that is performed on the heat pump, this is the input of work, is 6.3 times 10 to the 6 joules. Of course, we're not really interested in W. What we're really interested in is QH. We're interested in the amount of heat that is pumped into the home or into the hot reservoir. Recall that for a heat pump operated in heating mode, the coefficient of performance is defined as QH divided by W. Rearranging this equation, we find that QH is equal to W times COP. We know W is 6.3 times 10 to the 6, and we know COP is 4.2. That's given to us in the problem. So the total amount of thermal energy that is pumped into the hot reservoir or into the home in 1 hour is 2.646 times 10 to the 7th joules. Let's continue the same practice problem. Part B of this question asks, if the heat pump is reversed so that it acts as an air conditioner in the summer, what would be its coefficient of performance? So we can essentially take the same heat pump, and by changing the plumbing, the direction of the flow of air, we can use it during the summer to cool our home. So we're still pumping energy from something cold to something warm. However, now the interior of the house functions as the cold reservoir. What we want to know is what the coefficient of performance would be in cooling mode. The first thing we need is this particular equation. Recall that conservation of energy implies that for heat pumps and heat engines, the absolute value of QH must equal to the absolute value of QC plus the absolute value of W. If you're using heat engines versus heat pumps, the W, the QC, and the QH will have opposite signs, but once you put absolute value signs around everything, you don't need to worry about the negative signs too much. Now also recall that the coefficient of performance for a heat pump in cooling mode is defined as QC over W. Recall that in cooling mode, the thing we want to maximize, the good stuff, is QC, and the thing that we want to minimize, the thing that costs us money, is W. So the coefficient of performance in cooling mode is defined as QC over W. Using this equation on top, we can write QC as QH minus W. So the coefficient of performance is QH over W minus W over W. So I'll write that as QH over W minus 1. Now from the previous slide, recall that QH over W is just a coefficient of performance in heating mode. When we're operating the heat pump in heating mode, the thing we want to maximize is QH, the amount of heat that is transferred into the hot reservoir. So COP in cooling mode basically becomes COP in heating mode minus 1. We know COP in heating mode is 4.2, so COP in cooling mode will have to be 3.2. And that is the end of this lecture. Thank you for your attention.